Module 3, Lecture A, Lists and Tuples. By the end of this lecture, you will be able to store ordered civil engineering measurements in lists and retrieve them by position. Use tuples to represent fixed engineering pairs or records, such as coordinates and dimensions. And process list data to compute summaries such as differences, totals, and averages. List storage. Creating measurement lists. In civil engineering, measurement lists keep observations in order and organize related data, such as field readings, into a clear record. A well-designed list does more than store numbers. It helps model a field log or dataset so the information is easier to manage, interpret, and analyze. Measurement lists are useful only when entries are recorded in a consistent way. Values should use the same type, units, and sign convention so they can be compared directly during analysis. Mixing different measurements or unconverted units can cause confusion and errors, so civil engineering data must be organized clearly in field books and spreadsheets. When engineers build measurement lists, the order of the entries must be clearly defined. That order may represent time, location, or the sequence of a test, and it determines what each position in the list means. Defining the sequence makes data retrieval meaningful and supports accurate engineering analysis. Python code. Creating measurement lists. Lists store ordered engineering measurements, with each value using the same unit. The position of each value makes it easy to retrieve specific recorded observations. We create a list to store weekly settlement readings in millimeters. Each value is a floating point measurement, and keeping them in a list preserves their time order. This makes it easy to track changes over weeks and analyze individual readings later. A list is used to store 4 slump measurements in inches. Keeping the values in a list preserves their order, making them easier to retrieve and analyze later. Use the length function on the settlement list to find how many readings it contains. This count helps identify positions in the list, including the most recent reading. The process gets the first settlement reading from the start of the measurement list, then finds the most recent reading by using the list's total count to locate the last item. This approach always returns the latest recorded value, even when the number of readings changes. To get the second slump measurement from a Python list, use the second position by referring to index 1. This works because Python lists start counting at 0, so index 1 selects the second recorded value for analysis or reporting. The output summarizes the settlement readings in millimeters, including the total number of readings, the first measurement, and the most recent one, to show change over time. It also displays the slump readings in inches and highlights the second slump value for comparison or further analysis. This script stores engineering measurements in lists and produces a quick summary of the data. It counts the settlement readings, retrieves key values such as the first and latest settlement measurements, and identifies the second slump measurement. When run, it prints a concise overview of these collected readings. List indexing. List indexing lets engineers retrieve a specific measurement from an ordered set by its position. This matters when the order carries meaning, such as finding a particular borehole sample or the final result in a test series. By using indexes, engineers can quickly access the right value while preserving the context of the data. Many programming languages count list positions starting at 0. So the first item is index 0, and the third item is index 2. This works because an index represents an offset from the start of the list. Remembering zero-based indexing helps prevent selecting the wrong value or labeling data incorrectly during analysis. Indexing supports engineering quality control by tying data to specific locations or testing stages. It works well only when the order of measurements is clear and consistent, such as for settlement readings, beam deflections, or water levels. If the order is uncertain, an index may still find a value, but the engineering meaning can be lost. Treat indexing as a disciplined way to connect numerical data with the measurement sequence. Python code. List indexing. Lists keep measurements in the order they are stored. Indexing lets you retrieve a specific measurement, and in Python, list positions start counting at 0. Pavement thickness measurements are stored in one list, while a second aligned list stores the corresponding measurement locations, such as the left shoulder or center line. Because the lists use matching positions, each thickness value is linked to the correct physical location. The code first checks that the thickness measurements and locations lists have the same number of entries, so each measurement has a matching location. If the sizes differ, it raises a value error. This prevents indexing mismatches later in the code. Python lists use zero-based indexing, so the first item is at index 0. The centerline measurement, as the third item, is accessed with index 2. To find the last item in any list, use the list length -1, which gives the final valid index, no matter how long the list is. Each numerical index is matched to its location label by looking up the corresponding entry in the locations list. This assigns labels for the left shoulder, center line, and right shoulder, so each measurement is clearly tied to its physical position. We extract pavement thickness values from a list by using stored positions for the left shoulder, center line, and right shoulder. This selects the key measurements needed for later analysis or reporting. The output first shows the full list of pavement thickness measurements to establish the data being used. It then highlights 3 key positions: the first measurement, the centerline measurement, and the last measurement, giving each one's index, label, and value in inches. This connects list indexing to the physical locations and their measured thicknesses. Zero-based indexing means Python starts counting list positions at 0, while people usually start at 1. So an item with index 2 is in the third physical position. This example highlights the key difference between programming indexes and everyday counting. The code performs a simple pavement thickness check by comparing the centerline measurement with the first measurement. It subtracts the first thickness value from the centerline value, then prints the difference in inches to show whether the centerline is thicker or thinner. This script shows how list indexing connects pavement thickness measurements to their locations. It first confirms the measurement and location lists are the same length, then uses zero-based indexing to access the first, centerline, and last thickness values. The example emphasizes that the third physical position is stored at index 2, and it finishes by comparing the centerline thickness with the first position as a simple engineering check. Storing measurements. In civil engineering, measurements often need to stay in the order they were collected, such as by time, depth, or location. Lists are useful because they keep related readings together while preserving that sequence. This makes analysis clearer, reduces mistakes, and keeps the data reliable for future use. When storing measurements in a list, The order of the values is part of the meaning. In engineering, that order may reflect a survey route, testing sequence, station numbers, or time steps. A list stores only the values, so you must add them deliberately in the sequence that matches how the data will be interpreted. When storing measurements in a list, keep units, precision, and sampling intervals consistent. Mixing units or measurement bases can cause confusion and calculation errors. A list is useful only when each position is clearly understood, so careful planning, consistent entry, and clear documentation make the data reliable for analysis. Python code: storing measurements. Lists keep engineering measurements in order, so each value stays connected to its field location. Using consistent units makes the stored data easier to retrieve reliably. Rut depths are stored in millimeters in the same order they were surveyed. This keeps each route segment's measurement organized and easy to access for later analysis. A list of survey segment names is created to keep track of the measurement locations. The segments A, B, C, and D are stored separately, so each measurement can be clearly linked to its correct segment and referenced easily later. The code first confirms that the number of rut depth measurements matches the number of road segments. If they do not match, it raises an error to prevent misaligned data. This check helps ensure every segment has one corresponding measurement and keeps the dataset reliable. Specific rut depth measurements can be retrieved by using their position in the list. For example, the first position gives the first rut depth, and the third position gives the third rut depth. This lets you store selected measurements directly based on their order in the list. The code prints the rut depth measurements and then retrieves values for specific road segments, such as the first and third segments. This shows that the position of each item in the lists matters because the segment order gives the rut depth data its correct meaning. Add the new rut depth measurement of 6.4 millimeters to the depth list, then add segment E to the segment list. Keeping both additions in the same order preserves the link between each measurement and its corresponding segment. To get the most recent measurement, find the last position in the rut depth list and use that same position to retrieve both the segment name and the rut depth value. This keeps each measurement matched with its correct segment and preserves the order of the data. The code gives quick feedback after adding a new segment by showing its rut depth in millimeters. It then reports the total number of stored measurements and lists the current survey order, helping confirm that the data is complete and correctly sequenced for later analysis or reporting. The script demonstrates how a list can store rut depth measurements in millimeters for road segments A through E. It first checks that each segment has a matching measurement, then retrieves selected entries to show how order gives the data meaning. After adding the final measurement for segment E, it confirms the update and reports the total count, highlighting that lists preserve survey sequence. Tuple records, coordinate tuples. Coordinate tuples represent related location values in a fixed order, such as horizontal and vertical position or elevation. Keeping these values together makes a point easier to store, retrieve, and use as one unit. Because each position in the tuple has a specific meaning, changing the order changes the meaning of the coordinate. Tuples are useful for fixed coordinate records in engineering because they treat a point as one complete, unchangeable unit. This helps prevent accidental changes to individual values and keeps each coordinate in its proper place. When a location must change, creating a new tuple makes the update clear, while preserving the idea that tuples are best for stable records like control points. Coordinate tuples provide a consistent way to represent engineering locations, such as points in a road alignment or building layout. Each tuple identifies one point, while a collection of tuples represents many points, making it easier to plot data or measure distances. This structure reduces confusion by clearly showing whether a point is two-dimensional or includes elevation, helping connect numerical data to real-world engineering decisions. Python code coordinate tuples. Coordinate tuples keep related location values together, with each position in the tuple carrying a specific engineering meaning. Because tuples are fixed records, they help prevent accidental changes to coordinate data. Fixed, two-dimensional survey coordinates can be stored as tuples, which keep related east and north values together and prevent them from changing. In this example, one tuple represents a benchmark point with coordinates 125.4 and 82.7, while another represents a column point with coordinates 140 and 96.5. The coordinate pairs for the benchmark and the column are unpacked into separate east and north values. This makes each coordinate easy to access for later calculations or comparisons in engineering work. To find the coordinate change from benchmark A to column B3, subtract benchmark A's east and north coordinates from the corresponding coordinates of column B3. The results show the shift between the 2 points in the eastward and northward directions. A three-dimensional point is stored as a tuple containing east, north, and elevation values, keeping the related measurements together. The tuple is then unpacked into separate variables, so each component can be accessed and used individually, such as the elevation in later work. The coordinate records are organized in a single list that includes benchmark A, column B3, and the horizontal coordinates of the inlet point, while leaving out elevation. The total number of records is then found by checking the list length, making it easier to manage and reference the available coordinate sets. This section prints the coordinates for benchmark A and column B3, then calculates their east and north differences, rounded to 2 decimal places and reported in meters. It also prints the inlet elevation and counts the stored site points, giving a quick summary of the fixed coordinate records being used. This script shows how tuples can store fixed survey coordinates safely. It defines 2 points, calculates the east and north changes between them, and reports the results rounded to 2 decimal places. It also reads the elevation from a 3-dimensional point and counts the coordinate points in a grouped collection. Using tuples helps protect the coordinate data from accidental changes. Tuple storage. In civil engineering, tuples are useful for storing fixed sets of related values, such as survey coordinates or beam dimensions. Each position has a specific meaning, so keeping the order consistent helps prevent confusion and processing errors. This makes tuples a good choice when data must stay stable, predictable, and clearly organized. Tuples are useful when engineering data must stay fixed after it is recorded. Unlike lists, they prevent changes to stable values such as borehole coordinates in geotechnical surveys. Treating these records as single, unchanging units helps maintain clarity and reduces errors as data moves through surveying, processing, and design. Tuples help engineering projects store fixed, structured data such as coordinates, dimensions, or locations. Because each tuple keeps its format stable, collections of tuples can manage many records consistently for processing, reporting, plotting, or comparison. This reduces ambiguity and makes engineering data clearer and more reliable. Python code Tuple storage. Tuples are useful for storing fixed engineering records, where each position has a specific meaning. Lists can then be used to hold many of these tuple records together. Borehole locations are stored as fixed coordinate pairs using tuples. In each pair, the first value is the easting, and the second is the northing. 3 boreholes are represented this way, giving each location a consistent and reliable structure. Create a list to store the borehole coordinate records as tuples for boreholes A, B, and C. Keeping these records in one list makes them easier to manage and access. You can then use the length function to count how many borehole records the list contains, which helps with iteration or checking the data size. To work with the first borehole location, take the first coordinate pair from the list and separate its 2 values. The first value gives the easting and the second gives the northing. This relies on the agreed order of values within each coordinate pair. Tuples are used to group fixed engineering measurements. A beam can be represented by its width and depth in inches, while a plate can be represented by its length, width, and thickness in millimeters. Because tuples are immutable, they are well suited for storing dimensions that should remain together and unchanged. The output displays the stored borehole coordinates, the total number of records, and the first easting and northing values to verify the location data. It also shows the beam width and depth in inches, followed by the plate length, width, and thickness in millimeters. Together, these prints provide a concise check of the key coordinate and dimension data stored in the tuples. This script shows how tuples can store fixed engineering records clearly and compactly. It uses tuples for borehole coordinates, groups them in a list, counts the records, and retrieves the first boreholes easting and northing. It also stores beam and plate dimensions as tuples, then prints these values to demonstrate how tuples work well for data that should stay fixed. Fixed dimension records. Tuples are useful for fixed engineering records because they keep related measurements in a consistent order. For example, a beam's length, width, and depth can be stored as one meaningful record. This makes the data easier to interpret and process reliably. Tuples are useful for engineering records because they keep related values in a fixed order and prevent the structure from changing. This helps dimensions such as diameter and thickness, or length and width, stay connected and correctly interpreted. They are well suited for design catalogs, survey descriptions, and standard component sizes where consistency matters. Fixed dimension records, such as tuples, help civil engineers store and compare component dimensions consistently. For example, bridge bearing pads or culvert sections can be recorded as complete sets of key measurements, making retrieval and comparison easier. The main value is a clear, shared structure for dimensional data, which reduces ambiguity and supports reliable engineering workflows. Python code, fixed dimension records. Tuples are useful for storing fixed engineering dimension records, where each position carries a specific meaning. Lists can then be used to store many of these tuple records together. Tuples are used to store fixed bearing pad dimensions in a consistent order: length, width, and thickness. 3 records are created, with 2 pads sharing the same length and width but having different thicknesses, and a third pad using larger length and width values. This shows how tuples can efficiently represent simple, fixed dimension records where each position has a specific meaning. A list of bearing pad records is created to store the fixed dimension entries in one place. The length function is then used to count how many records the list contains, and the result is printed to confirm the total number of entries. The first bearing pad's dimensions are taken from the first tuple and assigned to length, width, and thickness in order. These values are then printed to confirm the pad's measurements. The first two bearing pad records are compared to check whether their length and width match. If both dimensions are the same, the comparison result is marked as true, and a message reports whether the two pads have the same footprint. The process calculates each bearing pad's footprint area by multiplying its length by its width. It then finds the average area across all pads and prints the result in square millimeters. The first bearing pad's dimensions are converted from millimeters to meters by dividing each value by 1,000. A tuple comprehension creates a new tuple with the converted dimensions, and the result is printed to show the pad size in meters. This script uses tuples to store fixed bearing pad dimensions, with each record containing length, width, and thickness. It groups the records, reports how many there are, reads the first pad's dimensions, and checks whether the first two pads have the same length and width. It also calculates each pad's footprint area, finds the average area, and converts the first pad's measurements from millimeters to meters. Processing list data. Summarizing measurements. In civil engineering, summarizing lists of measurements helps turn raw data, such as settlement readings or rainfall depths, into useful information. Treating the values as one dataset lets engineers examine totals, deflections, and measurement patterns. The purpose is to support better engineering decisions, not simply reduce the data to one number. When summarizing data, compare measurements within the list to reveal overall patterns, not just individual values. Ordered readings can show trends such as changes in road elevation, widening cracks over time, or consistency in concrete test results. Unusual values become meaningful only when viewed in context with nearby or related data. Measurement summaries should explain both what the numbers mean and how they were collected. Totals describe accumulated quantities. Differences show change, and observation counts help indicate confidence in the results. These summaries give engineers a clear basis for analysis and help them communicate findings while staying connected to the original data. Python code summarizing measurements. Lists make repeated engineering measurements easier to organize and summarize. When values are ordered, they support quick totals, comparisons, and differences, helping reveal useful field patterns. Rainfall measurements are stored in a list, where each value represents the amount of rain recorded on a consecutive day. Organizing the data this way makes it easy to calculate totals and averages and to identify trends over time. To check that the rainfall data can be used for calculations, first count how many measurements are in the list. This total number of observations is needed for later work, such as finding totals and averages. To summarize rainfall over several days, add all the measurements to find the total rainfall, then divide that total by the number of measurements to find the average daily rainfall. This gives a simple view of both the overall rainfall and the typical daily amount during the period. To find the net change in rainfall, compare the first recorded measurement with the last one. Subtract the first day's rainfall depth from the final day's depth to see how rainfall changed over the full monitoring period. This gives a simple view of the overall trend from start to finish. We begin by creating an empty list to store the day-to-day changes in rainfall. This will hold the differences between each pair of consecutive measurements, helping us track how rainfall changes from one day to the next. To find daily rainfall changes, compare each measurement with the one before it, starting from the second day. The difference gives the change from one day to the next, and each result is added to a list of daily variations. The summary presents the rainfall data by showing the recorded measurements, the number of observations, the total rainfall, and the average rainfall in millimeters. Together, these values give a quick overview of how much rain was measured and what the typical daily rainfall was during the monitoring period. The net change in rainfall is found by comparing the last measurement with the first, giving an overall view of how rainfall shifted over the period. The daily changes show how rainfall differed from one day to the next, helping reveal short-term variability. This script analyzes rainfall measurements collected over consecutive days. It reports the total and average rainfall, the overall change from the first day to the last, and the day-to-day changes between measurements. Together, these results give a concise summary of the rainfall pattern over the observed period. Summarizing list values. In civil engineering, summarizing list values means turning ordered measurements into useful insights. By reviewing data such as concrete slump or river levels over time, engineers can track patterns, estimate material use, spot changes, and identify possible stability or quality issues. This helps convert detailed observations into practical information for decisions and quality control. Engineers often summarize lists by finding totals or differences. Totals show an accumulated amount, while differences show how values change across distance or time. These summaries turn raw measurements into useful insight about performance and change in engineering systems. When summarizing lists, choose summaries that match what the data represents and how it is organized. Totals only make sense for values that can be meaningfully added, while differences are most useful for consistent or sequential measurements. Engineers should also check for missing values, outliers, and unit mismatches, because these can distort results and lead to poor decisions. Python code, summarizing list values.
Summaries help turn measurements into useful engineering information.
Lists organize field readings, and Python can quickly total, average, and compare those values. We store daily concrete delivery amounts in a list of truck volumes measured in cubic yards. Keeping the data in a list makes it easy to calculate totals and averages for later analysis. First, find the number of truck volume readings by using the length function on the list. This total tells us how many data points we have, which is needed for calculations such as finding averages. Before calculating summaries, the program first checks that there are truck volume readings available. If the list has at least one entry, it continues with the calculations. This prevents errors or undefined results from trying to process an empty list. To find the total concrete delivered, add all truck volumes using the sum function. The result gives the total delivery amount in cubic yards, which supports logistics planning and further analysis. To find the average concrete volume per truck, divide the total volume delivered by the number of readings. This mean value gives a simple summary of the delivery data. A list comprehension can be used to find how truck volume changes from one day to the next. It compares each reading with the previous one and stores the differences, producing a list of day-to-day volume changes. The output summarizes the concrete delivery data by showing the truck volumes, the total amount delivered, and the average load rounded to 2 decimal places. It also reports how each delivery volume changes compared with the previous truck, giving a quick view of the main statistics and trends in the dataset. A list is created to store elevation measurements in meters. Keeping the survey elevations in order makes it easier to compare values and analyze changes between consecutive points later in the code. To find elevation changes between stations, compare each elevation with the one before it. A list comprehension can do this by moving through the elevations from the second value onward and storing each difference in a new list. The code summarizes previously calculated elevation changes in meters and reports the average elevation. It finds the average by adding all elevation readings and dividing by the number of readings, giving a clear overview without too much output. This code checks whether the readings list is empty before trying to summarize it. If there are no readings, it prints a clear message for the user instead of performing invalid calculations. This helps prevent errors and keeps the program's output understandable. The script summarizes daily concrete deliveries and survey elevations when data is available. It calculates total and average concrete volume, compares consecutive truckloads, and reports elevation changes along with the average elevation. If no readings are present, it states that there is no data to summarize. Overall, it provides a concise view of averages and changes in sequential measurements. Averaging measurements. Averaging helps civil engineers condense multiple measurements into one value that represents the general level of the data. This is useful because readings can vary due to instruments, materials, or site conditions. The average gives a quick sense of typical results and supports early analysis and decisions, but it does not mean every measurement is the same or that unusual values should be ignored. To find an average, add all the values in a list and divide by the number of entries. The result describes a typical value, but its meaning depends on what was measured, the units used, and how the data was sampled. A well-organized list helps ensure the values are processed consistently. Averages are useful, but they can hide important variation in engineering data. Pavement or beam deflection may look acceptable on average while still containing weak or problematic readings, and concrete strength may appear adequate even when some tests fail. To understand performance more reliably, use averages together with measures such as totals, differences, and extremes, so both the overall trend and key inconsistencies are visible. Python code, averaging measurements. Lists can hold repeated engineering measurements, while averages provide a quick sense of the typical level. However, the individual measurements still matter because they preserve the detail behind the summary. We store 5 slab thickness readings in inches: 5.9, 6.1, 6.0, 5.8, and 6.2. Keeping the measurements together makes it easy to calculate the average and compare each reading with that average. Use the length function on the list of slab thickness readings to find how many measurements were taken. This count is needed to calculate the average thickness by dividing the total thickness by the number of readings. To find the total slab thickness, add all the thickness readings using the sum function. This gives one combined measurement, which is needed later to calculate the average thickness. Average thickness is found by adding all the thickness readings and dividing by the number of readings. The result is one value that represents the typical slab thickness from the measurements. This step finds how far each slab thickness reading is from the average thickness. A list comprehension subtracts the average from each measurement to create a list of differences. These differences show how much each reading deviates from the average and help reveal variability in the data. The output summarizes slab thickness measurements by showing the readings, the number of measurements, the total thickness, and the average thickness, with key values rounded to 2 decimal places. It also shows how far each reading is from the average, helping reveal the variability in the data. This script analyzes slab thickness measurements in inches by finding the total, calculating the average, and comparing each reading to that average. When run, it prints a concise summary showing the original readings, the number of measurements, the rounded total and average thickness, and the rounded differences from the average. This helps quickly show the overall thickness data and how each measurement varies from the average. In this lecture, you learn to store ordered civil engineering measurements in lists and retrieve them by position. Use tuples to represent fixed engineering pairs or records, such as coordinates and dimensions. And process list data to compute summaries such as differences, totals, and averages. In the next lecture, Lecture B, we will go over dictionaries and sets. Thank you for your attention. See you all in the next lecture.